Well, good afternoon, good evening, everybody, and welcome back to SETI Live. My name is Simon Steele. I'm the Deputy Director of the Carl Sagan Center at the SETI Institute in downtown Mountain View, California. And I'm wonderful to be joined by Lauren Sgro, who is over the other side of the country in Athens, Georgia. Georgia. Thank you. That's a first mistake down for the day.
Yes. Hi.
Good to see you again. So we are going to be talking about an amazing citizen science observation made by the Unistellar telescope network. I suppose we should say that this whole story started a long time ago in a galaxy far away. In fact, 21 million light years to be exact, when, and 25 million years ago, when this very large star decided to go supernova. That light has traveled for 21 million years across space and was captured by a set of EV scopes run by the Citizen Science Program, of which Lauren is a coordinator and lead. So we're going to go back along that photon path and talk more about the galaxy and the supernova a little bit later on. But Lauren, tell us a little bit about your role, a little bit about Unistellar, and especially about the telescope that made these observations. I have one behind me here for a sense of scale. This is
Yes.
scope. So say a little bit about these telescopes.
Yeah. Hi, everybody. It's wonderful to be here, and having a telescope for scale in your background means that you are definitely an astronomer. So my name is Lauren Sgro, and I'm a citizen science researcher with the SETI Institute and also an outreach coordinator with Unistellar. So that beautiful Unistellar telescope that's behind you, Simon, is capable of taking scientific data. Everything on the telescope is run through an app on your phone or your tablet. So in that way, SETI and Unistellar are kind of trying to democratize astronomy and make it accessible to everybody. And that's really what the Citizen Science Network is about. So anybody with a unistellar telescope, which can include people in schools, people just at home who have the telescope and use it to do science or to just observe, can participate in these citizen science programs. So on the SETI side, we have several researchers leading different aspects of the citizen science programs, which include everything from asteroids, exoplanets, comets. I feel like there's something else I'm forgetting. Oh wait, supernovae, and other transient cataclysmic events. And anybody with the telescope can observe, and we all communicate on a Slack forum where we have 2,000 active members, so people always chatting. There's always a clear sky in the SETI Unistellar network, so there's always somebody observing some sort of scientific endeavor.
Right. So there's always a clear sky somewhere in the world, except for San Francisco,
Exactly.
it seems to be, and in southern England, as I know from experience.
Yes, all the fog.
Yeah. So I see a lot of people have told us where you're tuning in from. That is wonderful. We have Morty from Normandy, who is an EV scope user. So a lot of this you're going to be very familiar with. We got people tuning in from France, from California, sunny San Francisco, Palmdale, California, and I'm going to scroll one down, Vienna in Austria. So welcome. Do keep saying where you're tuning in from. And if you do have any questions for Lauren, we'll get to your questions a little bit later. Again, pop them into the comments, and Beth and Rebecca, who are behind the scenes, will be sorting those questions out so we can get round to addressing those. Lauren, let's go back. The supernova, which has the very romantic name 2023 IXF. Maybe you want to say about how supernovae are named in a second. This was discovered on May the 19th, 2023. So when did Unistellar get involved? So you didn't discover the supernova. How did you find out about it, and how did you rally the troops, as it were?
Sure. It's actually a little bit of a funny story. The troops rallied themselves, and we kind of helped. I mean, this is really just a wonderful example of citizen astronomy, citizen science doing its thing. So on May 19th, a amateur astronomer in Japan, Koichi Edagaki, he discovered this supernova serendipitously while he was observing the pinwheel supernova, the pinwheel galaxy, which, like you said, is 20 million light years away. It took a while to reach us, but is still basically the closest supernova of the last decade. And we started observing about a day later, which is really quick. So the next night, basically, our Unistellar network members were on target observing and sharing the good news of the supernova with each other and with everybody else. What's interesting about this supernova is we have a cosmic cataclysms alert system. So cosmic cataclysms is the name of this science program in the Unistellar network. And it utilizes alerts from the Zwicky Transient Facility, which is essentially a telescope facility that is searching the night sky all the time for transient events, which are, high energy events that come off and on. They're quick and they're going to fade. And this particular supernova was not classified as a supernova by the Zwicky Transient Facility. Man, that rolls off the tongue just like 2023 IXF. Yeah. And so it was really up to our citizen astronomers who were watching the news and watching that that Itagaki had posted that he had found the supernovae, and they took to the races and started observing right away.
Okay. Because supernova, I mean, it's a random event. I mean, for a particular star, it's not random. But seeing a supernova, detecting a supernova, they're reasonably rare. I think about once every 30 years or so in any particular galaxy of 300 billion stars. So they're going to go off, but it's still something that amateur astronomers can play an active role in, isn't it? One of the strong areas.
Absolutely, and it's particularly important, and that's where the Unistellar and SETI network is really important in these types of cases, is that oftentimes we're waiting for a bigger facility to have time to observe a particular object. But when you are an amateur astronomer, you can hop right on target, and that early data right after the supernova is detected is the most important data because it tells us some really interesting information about the explosion itself. So that is where people can really, really help science as a whole by getting right on target and also continuing to observe. Like I said, there's always a clear sky in the Unistellar network. So people aren't necessarily always set back by the weather. So amateur astronomers all over the world participating is incredibly helpful, particularly for this area of astronomy.
Yeah. Nice. Do you have an image of the pinwheel galaxy for us?
Yes, absolutely. Yeah. If we could go to, I have a few slides actually of some of my favorite images from the observers. So this one is quite a beauty, if I do say so myself. I believe this was taken by one of our astronomers in Canada. And I think that there's a few more as well. Let's see.
So this is for people to, this is a face-on spiral galaxy, not too distant. Nevertheless, it's quite a faint object, isn't it? It's what they sort of quite a low surface brightness, as astronomers would say, and that's where the Unistellar telescope comes in to play, because it can basically build up the image over time. Most telescopes, unless you've got quite a sophisticated camera attached to it, you can't get these sort of deep images. Can you say a little bit about how the EV scope picks up? How would you take this image?
Sure, yeah. So we have a mode basically that's called enhanced vision. And when you are on target, you basically select the object you want to go to, you press a button and the telescope goes there by itself. And then you can activate enhanced vision, which is essentially the telescope taking some exposures and then adding them together over time. And then we have a light pollution reduction. We're basically using machine learning to select the light that we want to see from the actual object instead of the light pollution from man-made objects. So we're stacking lots of images together, gathering more light over time so you can see details that you typically wouldn't be able to see. Tried to observe this with a regular Dobsonian telescope and you can't see a whole lot. So it's really fantastic what this telescope can do and help us to see.
Yeah. So you got the galaxy here, you got those stars in the field as well. Those are the bright white dots, and you've got the nucleus of the galaxy, which is a slightly larger bright dot. So how looking at that, how would somebody say, there's a supernova going off in this galaxy? What's the process there for identification?
Yeah, so I think there's actually another set of images
Mm-hmm.
here. Yeah, let's see if we can wait for it. It should be in. There we go. Awesome. This is just I have some arrows here, which makes things a little bit easier. Yeah, so you would basically just compare images from the supernovae taken, at a certain time before, and when you again maybe process an image like Itagaki was doing when he discovered it, you would see a very bright spot appear that can sometimes be brighter than the entire galaxy. So you can see here where these arrows and selections are pointing, that wasn't there when before the supernova occurred. So you're seeing a real itself is not observable in the entire galaxy unless it's going supernovae.
Yeah. So you've got one star. Fortunately, there's a 20,000 light year long orange arrow also in that galaxy.
Yeah, not to scale.
Yeah. So, I mean, when this thing goes off, as you say, it's just one of billions of stars, and suddenly this one star is lighting up, as bright as millions of stars. But it's still a point source, isn't it? Because it's so far away.
Correct. And
Yeah.
that's what makes it easy to pick out in the images and in the data.
Right. So lead us through the observations, because it's been detected. The network has come alive.
Yes, the network has come alive.
And so now you begin your set of observations of this source of light, this supernova that has gone off. How many? First of all, what's the size of the observing population here, and where are people scattered? Where are people joining this network from?
Yeah, there's actually a map that I can show you. So yeah, perfect. So once we started science observations of the supernova, we had about 123 people observe over the course of a little over a month. And they were scattered all over the world, in North America, Europe, Japan. And because of their being so spread out, we were actually able to have observations that were really, really close together. So we say that creates a really dense light curve. So for those of you who don't know, a light curve is just basically showing us how the supernova changes in brightness over time. And because we had people observing all over the place, their time difference as to when night occurs, we had observations going all the time with an average difference between the observation times of only about 4 hours. So there wasn't a whole lot of time that the supernova wasn't being observed by the Unistellar SETI network.
That's wonderful, because unfortunately we live on a rotating planet. So
Yes.
you observe with a telescope, and then suddenly it's daytime, and you've lost it.
It's unfortunate, yeah. But I'm glad that it's happening. I think that's what's keeping us alive. So. But yeah, this particular observation, 123 observers watching one astronomical event is actually a record for us in the SETI Institute as a citizen science network. This is the most people that we've had observe a single event, and that really helped to get the kind of data that we needed to see some real results from our science.
Right. And pulling the data together from all these different telescopes, you obviously have to pull them together. They will have to be time stamped. You
really
need
fun.
to actually how much is done by the trusty computer, and how much is done by the sort of poor human?
By the poor human. It really just depends on the situation, and from science case to science case, and from science program to science program. But we've had an amazing team who has built a lot of code that helps us to process all of this data in a timely manner, so that we can get these observations for a month and then basically turn it around and turn it into a publication or report, so that we can get it out to the astronomical community so that other people can use it. And that was really the goal here in getting some of this data published so soon. Was this is a wonderful opportunity for people to basically study something we don't get to see all the time. A supernova this bright means that amateurs and professionals get to collaborate and get data that we typically wouldn't be able to get because there's more telescopes on this object.
Yeah.
And we're able to share that with the astronomical community because of these wonderful people that spent their nights observing. I really don't think some of them sleep. I think maybe they sleep less than I do, which is not a whole lot. And it's a beautiful thing as an astronomer to see.
Yeah. We're going to go questions in a minute, but I think before we look at the data and the results, it actually quite ties in here with a question from RL, which is what is a supernova? What causes a star to go supernova? Because it would be nice to know the sort of mechanism before we try and interpret what the graph looks like.
Absolutely. So a supernova is basically the last breaths of a dying star. And there's several situations in different ways that massive stars can go supernovae, or white dwarfs can go supernovae, which is kind of like the dead core of a sun-like star. That's what a white dwarf would be. But a supernova at its core is an exploding star. But what's happening in these core collapse supernovae that we see, which is what this type of supernovae was, is typically that basically the star is running out of fuel. So stars are fusing hydrogen, and eventually when they run out of hydrogen, they're going to fuse helium, and then they're going to keep fusing into heavier and heavier elements. And when it finally starts to try to fuse iron, it's too much for the star to handle, basically. And that requires too much energy, and essentially the star completely implodes on itself.
Mm-hmm. Yeah.
And this can essentially lead, in cases of this type of supernova, to a neutron star or a black hole.
Depending on how massive that star is. So you got something much bigger than the sun. The sun can't go through this sort of process. We're fine, although that's a long time off anyway.
Yeah.
So there's sort of 10, 15, 20 solar mass star goes through a core collapse.
Exactly.
Core collapse supernovae, and then there's a rebound, and the outer envelope of the star is blown off into space.
Precisely.
And
and when that, sorry, go ahead.
Yeah.
I was just going to say, when that shock wave kind of extends past the surface of the stars, when we start to see that first optical indication that a supernova has occurred. But yes, you are absolutely correct. So massive stars, the sun won't go supernova, but massive ones like this will. And we're all lucky that the sun won't go supernova, I think.
So what you're measuring is the sudden brightness of this explosion, and then the gradual dying off, because obviously what's happening. We're running through this. In fact, let's pull up the graph, so maybe we can run through the timeline of this magnificent star's sort of dramatic Shakespearean death.
Yes. That's a great poetic way to describe it.
So what are the axes, first of all, on this? What are we looking at in this sort of quite a simple plot, isn't it?
Yes. So on the y-axis, so the vertical axis, you have a measurement of brightness called magnitude. On the left is apparent magnitude, which is how bright the star appears. And absolute magnitude on the right vertical axis is how bright the star would be if it were 10 parsecs away from us. And a parsec is about 3.26 light years. Not much to do with Star Wars. You may be thinking about the Millennium Falcon running the Kessel Run in 12 parsecs, but it's a unit of distance as well. So essentially, long story short, on the y-axis is brightness. And we can see the way that this graph is set up is that brightness is increasing towards the top of the graph. And on the x-axis, we have days since was about probably the first known detection. And the first known detection was actually a night earlier than Itagaki had discovered it. So people were looking through their serendipitous images and actually found evidence of the supernova before it was ever announced. So that's the 0 point on this x-axis. And you can see the purple data points are Unistellar and SETI observer observations. So we have quite a few on this plot. And you can see that brightness really, really increasing in a really, really short time right after the supernova was first discovered. And it peaks all the way at the top. And what's really wonderful about this data is that we were able to extract a peak magnitude from this data that is in strong agreement with that gathered by professional telescopes. So we're not only getting really highly sampled data, which allows us to model the supernova better, but we're also getting accurate data, which is really important and just shows the strength of citizen science here.
Yeah, and that's quite important. And I don't want to bring in UAPs, even though this is the but the important thing here when you're doing science is that you make observations, you make recordings, it's replicable, and other people can duplicate your results to confirm that the data you're getting is accurate, and that's how real science is done. It's no one person claiming they saw a supernova. This is something that has to be worked through.
Yeah, and what's actually really interesting about this, we were able to also gather serendipitous observations that people had taken with their unistellar scopes. So even though we didn't start observing in scientific capacity until about a day later, we actually have our first detection of the supernova only 5 hours after the very first known detection, which is super exciting as well.
That's amazing. It's a very fast climb, isn't it? The initial
Yes.
output, and then there's a gradual slope down. So, from that graph, what's the most recent point on that graph? And I presume you're still adding data points.
Yeah, we absolutely are. So we'll continue to observe this until it's no longer visible through the EV scopes. Definitely through August, perhaps even later. So the peak magnitude was at about 11th magnitude. And right now it's at about 12.5 magnitudes. So for, I was trying to think of some numbers to compare it to, but
that's right.
I can't think of any numbers off the top of my head. Like, what's an 11th magnitude star? It's dim, but it's much brighter than it was. So it basically increased a lot. And then we're now seeing it decline slowly but surely.
Yeah. So it's not something that it's always been too faint for you to just with your unaided eye. This is a telescopic event at that level. Yeah. And something for people who don't know the bizarre concept of magnitudes, of course, is that the bigger the number, the fainter it is, which is just a wonderful sort of cryptic thing that astronomers have invented. And so if you're 12th magnitude, you're actually not as bright as when you're at 11th magnitude, which is wonderful. And just to add mystery.
We love to make things so easy, and we love to name things, weird things. We love acronyms. Us astronomers are clever.
I'm going to just have a look at some of the questions here. Also, a few more people. We've got people watching from the Philippines, from Mexico, from the UK, Georgia. I don't know if that's the country or the state, so we'll take it as
probably my mom.
From Rio. So thank you everybody for tuning in here. So let's look at some of the questions. For a question from Sandy, at what point in the explosion is the supernova the brightest? I mean, that's something you can extract from the graph, isn't it?
Absolutely. So we actually saw from that graph that a few days later, a few days after that first known detection, we see that peak magnitude about a week later, about 5 to 7 days later. And at that point, basically all of the light that was created in this energetic explosion has pierced through all of the material that the supernova is shedding outwards. And that's what we call the peak.
Right. So we have a couple of questions about the benefits and hazards of supernova explosions. We'll get back to that in a little bit.
Sure, but, that's going to be interesting.
Just a question from Sydney. When the alert was raised, do telescopes automatically receive that command to point at it, or at what level is a human involved?
Sure.
In terms of, obviously, in terms of an EV scope, if you have an EV scope, what's your involvement once this is made?
Yeah, so there's multiple ways to watch and receive alerts, whether it's through online, following the facilities that are giving alerts. But if you were to have an EV scope, what you would basically do is just join our Unistellar network Slack channel. And that's where we're all communicating, where we're all talking and helping each other. And we basically take those alerts, which are a little bit, harder to understand, and we put them in a readable format that's super easily understood and give you all the information you need to know that something just happened, and then you can go observe it right away. And we have a website that does the same, basically. So there's machine and humans working together in this case to make sure that the right alerts are getting to everybody who wants to observe.
Yeah, excellent. Question from Stephen, and it may be too early. Is the progenitor star identified? And that's not easy, is it?
It is not easy, but it has been identified in, I believe, the Hubble and Spitzer images. So this is a red giant star, and it appears to have some sort of circumstellar, which just means around the star, shell of material that was hanging out around it before the supernova exploded, which has made for some interesting interpretations and modeling and trying to figure out exactly what happened. But yes, the progenitor star has been identified by other groups.
Okay, wonderful. So exciting. And if anyone wants to see what a red supergiant looks like, so can go out on the winter night and take a look at Betelgeuse.
Yes. That's the star that got me interested in astronomy. I was like, oh, what's that? And, it was all downhill from there, and here I am.
Wow. Okay. Okay, I'm going to read these ones now. What from Jess? Was this an extinction level event for any nearby civilizations? So
yes.
Okay, good. Okay, say more.
I would imagine so, that if there's any planetary inhabitants, if there were to be planets in that star system, which I don't know if there were, but that would absolutely be an extinction level event. That's something that planetary system would not be able to survive. These are some of the most energetic events in the entire universe. So yeah, they're toast, unfortunately.
Okay. And question from Doomsday Library, and this is supernovas, are they all bad? In fact, supernovae are quite important to life in the universe. Getting it back to this whole SETI mission, what is a supernova doing as far as its neighborhood is concerned?
Yeah, so because it's because these are such high energy events, these are some of the only instances in our universe where heavier elements can be created. So in that way, Carl Sagan was right. We are all star stuff, because a lot of the elements that are in our body and give us life are only created in supernova explosions.
Yeah. Yes, these are.
That's a really good question.
Star stuff. Yes, definitely.
Yes.
Question from Fadi. From this data, can we already figure out the mass of the progenitor star, or anything, whether it's a black hole or neutron star outcome?
Yeah, so from this data in particular, not quite. What we would need is to identify that progenitor in those Hubble and Spitzer images, which I was mentioning that other teams had done. And they have actually been able to estimate the mass of the progenitor star, and I believe that the outcome is most likely to be a neutron star as a result.
Okay, so it's big, but not
black hole big.
Not big enough.
Yeah, exactly. That was a great question.
Yeah, yes. We're coming up to time now. I just asked Laura, I suppose, what's next? There is another question about how long can we collect observational data? That's from Mario. So what's next is more of the same in terms of this source. But what next for the citizen science program at Unistellar? Do you have a next campaign lined up, or some of these are sort of can be out of nowhere?
Yeah, exactly. It's a little bit to Mario's question. So we'll continue to observe it for as long as we can see it, at least for the rest of the month, and probably longer, until it gets probably down to maybe like 15 magnitude, or maybe a little brighter. We'll see. But once we have as much data as we can possibly gather, we'll do another study on this system. And perhaps try to gather, even more results, and say even more about this particular supernova. But in the future, yeah, transient events you can't predict them, but we will continue to observe supernovae, and we'll also hopefully be able to help out with follow-up from the Vera C. Rubin Observatory when that comes online late 2024 and early 2025. So this will basically exponentially increase the amount of transient events that we're observing every night, or we as humanity are observing every night. Yeah. And there's just simply not enough telescopes to follow up all of those super interesting events. So we hope to basically receive those cosmic cataclysm alerts from Rubin and be able to help with some really interesting follow-up and get data even quicker for supernovae, and also potentially do some GRB follow-up. So a gamma ray burst is usually thought to be caused by the merger of a neutron star or a black hole, or black holes to be more specific. Those are really, really energetic events, and they often leave a bright flash that's really, really quick. And we're hoping to also potentially observe those in the future as well, try to get some really fast follow-up of these very transient events. Those GRB afterglows is what they're called. And even more science cases in the future. There's all sorts of transient events in the night sky. So the takeaway from that would basically, we'll keep observing this. We'll keep observing the supernovae that come down our alerts pipeline. We'll be excited for Vera C. Rubin, and we will continue to look at not more interesting, but more.
It's difficult to get more interesting than this, actually. But, yeah. Maybe an alien megastructure, but this is pretty interesting. Yeah,
that would be really cool. Now that would be cool. Yeah, we'll observe those too.
Yeah.
But yeah, more additional really interesting types of transience events in the night sky.
Nice, and it really does show how amateur astronomers. The citizen scientist, I suppose, is a new name for amateur astronomer in a way, isn't it? Because you can participate in these campaigns, and not just with if you have an EV scope, but there's with your local astronomy club with different types of telescopes, can really contribute to our understanding of the universe and these
100%.
Really big astronomical ideas. Yeah.
Yes, none of this would have been possible without any of the people that observed. So a big shout out and thank you to all of them, because they're really changing the way that astronomy and science as a whole is done now. And it's a really beautiful thing that more people are looking up to the skies and around them.
Okay. I think that's a wonderful comment to end on. Thank you, everybody, for tuning in. Do check out the SETI Institute website for future SETI Lives. Remember that we are a non-profit organization, do rely somewhat on donations, so keep that in mind. Lauren, lovely to speak to you. We will keep monitoring what Unistellar is doing, and obviously any future supernovae in your future, we'll be back talking about that. Thank you. Awesome. And thank you everyone for tuning in.
Thank you.